Okay, so the electric flux density D and the electric field for a free point charge. We have learned this in Coulomb's law. Okay, we know how to calculate that from Coulomb's law of the electric field of a point charge. And we can also calculate the electric flux density knowing the relationship between the electric flux density and the electric field. So we're now going to use Gauss' law to show or to see whether it's consistent with Coulomb's law. So we have a point charge that has a charge or free charge Q. And if we choose a Gaussian surface of a spherical or sphere that have a radius r, so we have a point charge, we choose a surface that is a radius r from the point charge. So meaning that from here, this has a radius r. And then we have a spherical Gaussian surface that covering this point charge. And then if we take the area element ds at any point on this sphere surface, we see that D is always parallel to ds. So any point of ds at any point, if we go around our spherical Gaussian surface, we find that ds is always parallel to the electric flux density D. And therefore the dot products of D vector dot with ds is equals to simply the magnitude of D times ds. We can remove the vector, okay, because they're in parallel. Dot product A dot B is equals to magnitude of A times the magnitude of B cosine theta, and because they are parallel, this simply equals to A B cosine of 0, and therefore it's equals to AB. Okay, so the dot product of D dot ds is simply equals to the magnitude of D times the magnitude of ds. And then we're doing a surface integral of these two products, and we know that from this point here, because the Gaussian surface is chosen so that the charge is set at the center of this spherical Gaussian surface, therefore the electric flux density at all the points on this surface is constant, and therefore we can take here, we can take D out of the integral. And this integral here is simply equals to the surface area of the sphere. And this equals to Q. So every point on the surface of the sphere is the same distance r from the charge. Hence the magnitudes of D is the same at all points on the sphere surface. So we can take it out of the integral, which is here. And then this integral is simply equals to the surface area of the sphere, which is 4 pi r squared. And therefore D equals times 4 pi r squared is equals to Q. And therefore the magnitude of D equals to Q over 4 pi r squared. Okay, so the electric flux density equals to Q over 4 pi r squared. And we know that D is equals to epsilon r epsilon naught times E. And therefore you can put E will be equals to Q over 4 pi epsilon r epsilon naught r squared. And that's what we have learned in Coulomb's law. Okay, so E equals to 4 pi epsilon r epsilon naught r squared. So here we have used Gauss' law to find D, And then you can use the relationship here to find E, and that back to our Coulomb's law as what we understand the electric field of a point charge. Okay, so in this case here, because we're treating it in the electric flux density, it doesn't matter whether it's a dielectric or it's a free space. It's the same because D is the same, because D only depends on free charge. So whether these materials here, whether it polarized or not, it has no effect in this equation because D only depends on this charge here, Q. And if it's polarized, then we can apply this relationship and work out the electric field by putting back the epsilon R value of the materials, the dielectric materials. Okay, there are some notes here. A positive charge like the one we consider here, the net outward flux D is a positive quantity. So D equals to a positive value if Q is positive. So what this tells you is that there's a net positive light charge, or there's a net outward flux that flow out from a Gaussian surface. Okay, so this case here, D lines is pointing outwards from the Gaussian surface. If it's a negative charge, then this line will point inwards and it's a net sink. Okay, so positive is a source, negative is a sink. So the sphere or the spherical Gaussian surface that we draw, there is a source of electric flux inside it. So there's a net flux flowing outwards. If it's negative, then there's net flux flowing inwards. Okay, so here is just a note to set that it doesn't matter whether that materials is dielectrics or not, because D only depends on free charge. So carry on from my slide, but I already said this. So if we found D, we can find E by applying the relationship. So D is equals to epsilon R epsilon naught E. And therefore, we can rearrange that for E. E will be equal to D over epsilon R epsilon naught. And we can find out the electric field of that charge. And if it's free space, then epsilon R will be 1. We substitute this epsilon R as 1 for free space. E will be equals to Q over 4 pi epsilon naught R squared. So this result tells us that the electric field of a free point charge with a dielectric takes the form as that in free charge, except you have a factor or reduced by a factor epsilon R, because of polarization of the dielectric materials. Okay, so what we have done so far, we only managed to calculate the magnitudes of the electric field. So to work out the vector, we simply multiply back our radial unit vector of a point charge, which is the A sub R unit vector, to make it back into a vector E. So that's for point charge. This is one of the examples that can be easily solved using Gauss law.